Hi, I'm Peter Cahoon and welcome to this series on construction processes for the RTA. Now get this, every year just in New South Wales, the RTA spend over $1 billion on construction. So to ensure long-term quality and durability, Don Carter here is going to let us know what is expected for RTA construction processes. Now Don, if there's one thing to remember to ensure quality and durability, what would it be?
Well, the main thing, Peter, I think, is that people have got to control the process. What we're after is we're building for the long term and we want the structure to last 100 years. And if the focus has to be on the 100-year life, not the now.
Now, my background's in architecture, and if I learnt one thing, it's all about the process and making sure you don't skip any important steps. And I imagine, Don, in this, it's very important to have the same sort of policy.
Exactly. And in the whole process, say, of construction, if any one of that part of the process is not right, one of those can bring you unstuck in terms of durability and, as you say, even structural integrity. And we can certainly look at an example from Quebec, where due to a number of issues, including low-quality concrete, reinforcement placed in the wrong place, that over a period of time this structure had an inbuilt deficiency which led to a complete catastrophic failure and in fact loss of life of people on the freeway below. But it really highlights that any one part of the process can bring the thing unstuck.
So everyone is responsible. Early on, all the way through, everyone's got to make sure they tie their laces properly.
Exactly.
So in this episode, we're looking at the 5 C's of concrete construction.
Yes, Peter, a very important concept. And there's a saying that says, good concrete is made from cement, fine and coarse aggregate and water, but sadly, so is bad concrete. The important thing is, it's the process that makes the difference.
And talking of good concrete, it's all about achieving durability.
Exactly.
So these are the 5 C's. First, a quick overview, then we'll go into more detail. Our first C, concrete mix design.
In this subject, we're looking at testing materials, testing the concrete mix, so we get the concrete that we're after.
Concrete production.
That's related to the actual batching of the concrete, transporting it to the site, and getting it into the job.
Okay, the third C is cover and content.
Yes, cover and content for Rio and Strand, because it's the cover that makes the difference. 5 mil of cover could add 15 years of life to the structure.
So on to the fourth C, which is all about compaction, and this is to do with the pour, isn't it, Don?
And I would probably say this is one of the most important aspects, compaction. So what we're after is about getting the density of the concrete so we get a durable, strong concrete in the structure.
On to the fifth C, which is curing.
So what we're trying to do here is to make sure we're going to provide sufficient water for the concrete to hydrate properly so that we end up with the material that we're after.
I think I'm excited, Don. I think I'm excited about concrete.
I never thought you would.
So in detail now of our 5C is concrete mix design. Don?
Certainly very important. What would normally happen is that the RTA holds a register of all approved concrete mixes. So the contractor, if possible, will probably go for one of those. But if he doesn't, then he's going to have to go through the process of preparing a new trial mix, doing all the testing to make sure that it complies. And also he has to make sure that it's suitable for the application to which he's putting it to.
Well, how do you make sure that it is suitable?
Well, on the drawings, there's a classification given to tell the contractor what the exposure conditions of the bridge will be, and that will automatically funnel him into a particular type of mix design to suit those conditions. He'll also need to know what the water-cement ratio is in the concrete, what the 28-day strength, how the concrete's going to be placed, whether it's going to be pumped, whether it's going to be put in with a kibble. So all these need to be assessed, and how he's going to cure the concrete.
So the water-cement ratio, this sounds important, Don. What is it?
Absolutely. So what the water-cement ratio is doing is defining the ratio by mass of water to the cement in the concrete. And ideally for high-strength concrete, we want low water-cement ratio, because the lower the cement ratio, the higher the strength. And that's why, we'll talk about later, if you start adding water to the concrete, you're changing the water-cement ratio, you're reducing the strength and you're reducing the durability.
Now, Don, let me throw this at you. What if someone specified a mix, a ratio, that wasn't on the register? What would happen?
If the contractor wants to use a mix that isn't on the register, he is then forced into going through the whole procedure of getting a trial mix approved, and that will involve testing the materials, all the cement, aggregates, etc., have to be all tested. He has to submit all this through a laboratory, but the thing that he has to allow for is that this process can take about 8 weeks for a new mix to be approved. But in terms of water-cement ratio, you can only vary that by 3%. So again, the contractor will weigh this up and say, no, this mix isn't going to suit me, I'm going to go and prepare a new mix because of a number of factors.
Now, the constituents of concrete can all have an impact on the final product. Let's go through some of the issues that can cause problems.
Yes, Peter, and one in particular that's worth mentioning, I think, is manufactured sands. Because of the lack of availability of some fine aggregates, crushed rock is now being used as a fine aggregate. The only problem with that material is that it has the potential to absorb moisture. So what happens is the concrete can be batched, be on site, and then absorption will occur. The water will take up into the fine aggregate. The concrete will lose workability, become very difficult to compact. And what it led to, in some instances, very severe cracking of a deck where the deck had to be removed because of the problem. So the manufactured sands have to be controlled, but the specification now requires that the absorption of the fine aggregate can only be 2.5% of the water.
Now, Don, supplementary cementitious materials.
That's a mouthful, isn't it? What we're talking about here are materials that are added as a supplement to the cement because we may want to control certain aspects of the concrete behaviour. So these supplementary cementitious materials will consist of fly ash, silica fume and other types of materials. The good part is that these are recycled materials, and so we're using a waste product for the benefit of the concrete as well as using it environmentally sound.
It's another language, isn't it, Don?
It is, but you're doing well.
Now, AAR, Don, this sounds interesting.
Yes, Peter, this is a situation that's arisen the last few years, and it refers to alkali aggregate reaction. And what happens is, as the concrete strengths have gone up, there's been a reaction between the silica in some aggregates and the concrete in the cement, and it produces a gel around the aggregate as it forms. And this gel is expansive. So over a period of time, and it may be 30 years, this will slowly increase this gel and literally blow the concrete apart, and also will allow the ingress of aggressive agents like chlorides in salt water, etc. And that will further deteriorate the concrete. And if you look at this section here of the concrete, you can see there's a piece of aggregate there with a distinct line around it, and that's the formation of the gel that will eventually damage the concrete. So to overcome the problem, all the aggregates now have been tested for reactivity to see whether they're susceptible to this problem. And so when a concrete mix is put together, they know whether they need to somehow address the problem.
And that's where our supplementary cementitious materials come in, if I'm not mistaken.
Yeah, and the actual material that's used is this material here, fly ash. And the beauty about the fly ash is that it's a recycled material, so there's a lot of it around. It comes from power stations. It has to be tested for compliance with standards, but the beauty is that the addition of up to about 20% of the cement actually stops this AR reaction occurring. And so we've gone from a problem with a material and we've corrected it with another material.
So the fly ash is quite handy.
Very handy, and in fact, if the designer of the mix has asked for this material to go in, it is very important that it goes in, because the implications if this is left out is that in, say, 30 years, the concrete will start falling apart.
Right.
So it's ultra important.
And the phone will start ringing.
Yes.
Now, did the Romans know all this, Don? Because look, we've got the basic ingredients here of concrete.
Well, actually, they did. They knew a lot about concrete, actually. And what we've got here is samples of the constituents of concrete. We've got the cement here that we use. This is the manufactured sand I was talking about that comes from crushing of aggregates. And this is a river sand that's used also as a fine aggregate. But the problem is today the availability of river sands is diminishing, and that's why the manufactured sands are being used. We have the fine aggregate that we use in the mix, and the coarse aggregate.
So they're the aggregates, Don, but we've got a couple of other beakers here that look quite interesting.
Yes, Peter. So the first one we've got here, this is a super plasticizer, and this is a very handy material that we use in concrete. We talked about before, we want the low water cement ratio for strength and durability, and by using a super plasticizer, makes the concrete very flowable, so you've got very flowable but very low water cement ratio. But the problem is that you have to make sure you use this material before what we call reversion, where the concrete slump will go back to the very dry mix, so you have to make sure you work the concrete, compact it before this material reverts and you've got normal concrete again.
So that's super plasticizer.
That's super plasticizer.
And some claret.
The other one we have here is a very good 1958 vintage, and that is a air entraining agent. Now if you look at this photograph here, Peter, you can see that there's a deterioration of that concrete rail, and this bridge is in a freeze-thaw situation. So what happens is if the concrete is designed with an air entraining agent, the air entraining agent produces discrete bubbles of air through the concrete, and so you end up with very small pores, but it's very impermeable to water. So in freeze-thaw conditions, the water won't penetrate into the concrete, because if it does, when it freezes, it expands and will blow the concrete apart. So an air entraining agent in cold climates is a very important admixture.
So that's the super plasticizer and the air entraining agent, but there are other admixtures as well, aren't there?
Yes, Peter, there are other admixtures that the designer of the trial mix may require, and that will be done to suit particular characteristics of the concrete. His options may include a water reducer of other types, it may be a shrinkage reducer, and there may also be corrosion inhibitors. But notwithstanding all that, the same situation applies, that if the admixture is being used, it's got to be tested, it's got to be dosed properly. So the whole thing, again, we're coming back to this control part of it. So the mix that's used has to accurately reflect those admixture requirements that have been specified.
And that's why the trial mix is so important.
Absolutely.
So I suppose the message here is to make sure that only approved mixes are used and that the components in those mixes are the same as the trial mix.
Exactly. And then any of the admixtures or any additives to the product has to be approved as well. And it may also be that the trial mix may have to be produced, say, for a column that's got a lot of congested reinforcing in it. You may have to go, say, to a finer aggregate because of the congestion, so that the concrete can get around the reinforcing steel.
So summing up our first C, concrete mix design, ensure that the trial mix is current approval, ensure that the proposed mix meets all the requirements of the design, and ensure that the components of the mix are as that tested in the trial mix, and that all materials used are tested for compliance or confirm that the approvals for their use are current, Don.
And as we said previously, if you don't know, ask.
Now, the second of the 5 C's is concrete production, Don.
Yes, Peter, and production is basically making sure that the correct mix is being used and the prescribed additives are being used as well, and basically it's controlling everything.
Now, moisture, critical.
Absolutely. The batching plant have to have a very good handle on what the moisture content of their aggregates is, because the amount of water that's added to the mix will vary depending on the amount of water that's in their aggregate. So they have to test it and then find out what the aggregate content, moisture content is, and then adjust the free water that they add.
So how do we monitor every aspect of this process, Don?
Well, Peter, the on-site staff have got to do a test, which we call the slump test, which is gives an indicator of the workability of the concrete, and also it tells us that if it's within a range that they're allowed. If the concrete arrives and the slumps way out of specification, then you might say, well, this is the right mix at the right place. So there has to be some checkings to make sure that you've got the right concrete.
Right. Is there any instances where this can be accidentally arrive on site and it's out of range?
Well, what can happen is a truck will arrive on site and the slump will be out of space, and there has been known for cases of people to go around the block and adjust the slump accordingly so that it comes back within spec.
No.
But they do.
Well, there's always someone to beat the system, I'd imagine. But getting back to moisture, I believe you can add moisture on site if you need to. And how much can you add?
Yes, you are allowed to add moisture. There's a few provisos on that. The first thing is that it has to be within 45 minutes since the cement was added at the batching plant.
Yeah.
It's got to be thoroughly remixed on site. Mm-hmm. And the water quantity is not to exceed 9 kilograms per cubic metre, and the water cement ratio is not to be exceeded. And the water quantity must be measured and recorded, and the slump still has to be within the range required, but no water can be added once the concrete truck starts discharging.
Now, the concrete's arrived on site, we assume it's all right, we've checked it, what happens now?
So once the concrete arrives on site, and I think we need now just to differentiate two things here, there's a difference between agitating and mixing. So when the truck leaves the batching plant, the truck is spinning at an agitation rate. So that's to stop segregation. But once it gets to the site, then you've got to mix it again. And if you look on and you can see here on this photo here, there's a plate on the truck that tells you what the mixing speed is and what the agitation speed is. And when you remix it, that has to be a minimum of 3 minutes.
How long does it take to become an engineer, Don?
Not long.
I don't believe you. Okay, the third of our 5 C's is cover and content of reinforcing steel and of pre-stressing strand. Don.
Yeah, and this is where we get to the stage where people really need to be hands-on.
Because what may look right isn't.
And as we said, don't trust your eye or the paperwork.
So Don, tell me about ACRS.
Peter, ACRS stands for the Australian Certification Authority for Reinforcing Steels, and it's a collaboration between government and industry whereby all testing is carried out on materials that come from overseas. The problem we have at the moment is we know where it comes from, but we don't know that it complies with our requirements. So what ACRS do is provide a certification for all these materials. So if you're on site, you need to have a certificate to say that it complies.
Yep.
And in addition, your responsibility on the site is to make sure that the number, location, and so the lap lengths of the bars all comply with the requirements shown on the drawings.
Sure.
All these matters need to be checked and marked off on either the drawings or a suitable checklist.
That's like our friends doing here. What are the other things you need to consider when you're inspecting the site?
Be very careful of the cursory glance. If you go and do an inspection without the specific aim of what you're going to look for, the chances are you won't see anything.
I see. What are they checking here, Don?
They're checking the pre-stressing ducts that are in the right location and securely tied to the reinforcement. Also, enough bar chairs need to be there to support the reinforcement, and the reinforcement strong enough to support the concrete workers and their gear.
Every time you turn up, you would assume that the site's clean, but not always the case, Don.
No, certainly not, Peter, because in the process of doing the construction, there's going to be accumulated rubbish, which may be blown in, or it may be bits of tyre wire, there may be bits of timber. And so what you've got to do is make sure that the formwork is clean and so that the concrete is not contaminated by rubbish.
So we've done everything. We've got the concrete there, we've checked it, we've made sure it's okay, we've got the formwork in, we've got the bars in. Are we ready to pour?
Not quite, because there are in some instances, say in a marine environment, where salt will be being deposited on the reinforcing steel while it's being built up in the cage. So that needs to be washed down so they remove all the salt. There may be overspray from curing compound in an adjacent area. There may be other contaminants So it needs to be cleaned down.
So much to think about, Don, before we start pouring, isn't there?
Exactly.
Now, I'd imagine atmospheric conditions are important.
Certainly very important. Whether you pour or not, you have to take into consideration what the atmospheric conditions are going to be on the day of the pour. And this can be due to wind, humidity, you may be getting rain. But in the B80 in the specification, you can see this diagram here, which gives a relationship between humidity, wind speed, and so it can tell you what the evaporation rate, and the specification will say the evaporation rate must be less than a certain threshold, so you have to check your conditions to make sure it complies.
And again, when these forecasts, this is all to do with your forward planning, I'd imagine, as well.
Exactly, and it may be in, say, adverse conditions in hot weather, you may want to start the pour very early in the morning, in the coolest part of the day, or if the conditions are extreme, you may have to do further pour till better conditions are available. So it's really being flexible about your pour and taking into account the weather conditions that are going to occur.
Now, Don, what about blinding slabs?
Well, a blinding slab is just simply a concrete slab that's put down before a member is poured as a support system for the reinforcing cage, the formwork, etc. So you've got a nice level working base to put your formwork on and control everything. So it's got to be strong enough to support all that weight that's going to sit on it. Now, the other issue that you have to make sure is when you pour the final concrete on top of the blinding slab has to be saturated. Otherwise, there's a problem that the blinding slab will suck moisture out of your new concrete. So you have to saturate that surface where there's an interface between the two.
So summing up the third C, concrete production, everything planned, everything to design, everything to the specification, everything checked before the pour. So on to the fourth C, which is all about compaction, and my understanding is the concrete mixes in, we've started to get the vibration happening, but I'm sure there's more to it.
There certainly is, Peter. And in fact, you could say compaction is a very important part of the process, because what we're doing is placing concrete from the truck that's got air in it, and what we're trying to do with the compaction is to get that air out of the concrete. And in fact, a 1% increase in air content reduces the compressive strength by up to about 3 MPa.
Makes a difference,
so it is significant. So the other issue is that if there's air voids left in the concrete, then that's a pathway for aggressive agents to get into the concrete and to the reinforcement. So again, we're talking about durability.
So that's the importance of compaction. How do we actually achieve it though, Don?
Well, really we need a systematic approach. You can imagine if you've got a large surface area that you're trying to compact the concrete, you have to remember that the vibrator has only an effective radius of about 250 millimetres. So you can imagine if it's not done systematically, it's very easy to miss an area of that concrete, and so you'll have concrete with air voids in it.
So I imagine the key tool here is the vibrator.
Well, no, it's not actually. It's really the operator, because the operator holds the key. He's the man holding the vibrator. And what the RTA has done in recognition of this is introduced what they call the grey card, where the people that are going to do the compaction have to be trained to do that task.
Now, us architects like to design all sorts of crazy things. How do you get the vibrator in and around those type of structures?
Well, certainly there's going to be some areas that are going to be difficult to get to, and it may require what we call a window in the formwork, where there's actually like a door, if you like, where the vibrator can be inserted into a difficult area, or it may need a small diameter vibrator. Conventionally, the vibrator is a 50 millimetre diameter, but you may need to go down to the smaller pencil vibrator to get into those congested areas. Now, in terms of a bridge deck, you can imagine if it's a very large area, you'll have more than one vibrator operating. So you've got a number of vibrators and obviously the operator. So this is where the complexity starts to come into, because how do you then control
who's doing what?
That area has been done, this area has been done, have you done that? So this is where things can go horribly wrong, and there's certainly been examples where due to a lack of compaction we've had problems with the decks. The other issue that comes up is in some members we use what we call a void former, and there's a real risk here. You can imagine if you've got a large circular void, there's a real danger of air being trapped underneath that that void former. So when it comes to this sort of construction, it has to be done very carefully, and we've got examples where there's been large areas of void because the concrete never got under the void.
We don't want that.
Exactly. And again, if it's an area that needs it, you may need to go to a smaller aggregate size. But of course, as we've said before, if we go to a smaller aggregate size, then we've got to go to another trial mix, if an approved one doesn't exist.
Now, Don, I'd imagine at the time of the pour, that's not the time to be introducing that.
Exactly. And that comes down to planning our process, doesn't it?
And you have to also plan for the failure of vibrators.
Certainly, and that's what's planning about, isn't it? So what the specification says is you must have one vibrator for every 10 cubic metres of concrete, and you've got to have one spare for every 4 vibrators. But also you must always use a minimum of 2 vibrators on any, irrespective of the size of the pour.
In terms of immersion time, it's just not enough to have the vibrators there to wait for the concrete to be level. That's not compaction. That's not good enough.
Certainly not, Peter. And compaction is in fact a 2-stage process. The first stage is where the immersion vibrator goes in, the concrete flows as a fluid, and the second stage is when the concrete starts to compact, the air starts to come out of the concrete, and so now we're into the proper stage of getting what we want.
You have to have the thing placed in vertically too, don't you?
Absolutely. So the concrete can only be best compacted if the vibrator is inserted vertically and then withdrawn slowly. Now, a good operator will know that when the vibrator goes in initially, there'll be a change in pitch, and then as the concrete is consolidated, that pitch will rise as the density of the concrete increases.
What about the times too? Because it's that fine a detailing in terms of how long you need the thing in there for.
So the initial stage where we talked about it becoming a liquid is about 3 to 5 seconds. The second stage where we're actually compacting it and getting the air out of it, normally about 7 to 10 seconds.
Wow, plenty to think about. I can understand why you need to be fully qualified for this role.
Exactly. And the other thing, people have also the thought that segregation may be a problem, so that you could over-vibrate. But generally, the modern mixes that we have today, segregation is not a problem. Our biggest problem is usually to do with under-compaction, not over-vibration.
And we have some examples here of what can happen when that attention has been missed. I know every aspect of the process is important, but it seems to me that compaction is the process that is potentially more prone to oversight.
Absolutely, Peter. And in fact, a very learned engineer, Dr. Neville, made a statement, and I quote, "In engineering practice, the strength of concrete comes down to 2 primary factors, water-cement ratio and compaction."
So to summarise the 4th C, compaction, plan the pour and compaction process, ensure concreters have grey cards, and supervise the workers to compact all areas. Now, the final C in our 5 Cs of concrete construction is curing. Now, there's a difference between drying and curing. Those terms aren't interchangeable, are they, Don?
Absolutely, Peter. So for hydration to occur in the concrete, moisture must be present. So if the concrete dries out, that hydration process will stop. And the chemical reaction that we require to continue to give us the strength and the durability has now stopped. And so what we're really saying is that curing allows for all the cement in the concrete to hydrate.
And hydration, Don, in this sense, isn't about getting a drink.
Certainly not. It's to do with giving the concrete sufficient water for the hydration process to go to its full extent, to ensure the concrete we end up has the strength and the durability for the purpose that we need it for. Curing allows all the cement to be hydrated. If we withdraw the water away from it by drying, the hydration process stops and we've got cement in the concrete that's unhydrated.
And here we're not talking in terms of hours, are we?
Exactly. So the curing has to be covered by 2 constraints, sufficient moisture and sufficient time. The specification says in the order of 7 to 21 days, depending on the conditions and the concrete that you've got.
Now, curing compounds, I know, are commonly used, but are they all they're cracked up to be?
Certainly not, but they are used in certain applications. We use them on the basis that we know they're not as effective as water curing, but in certain applications that is the best alternative. However, in the case of a bridge deck, where we've got such a big area, it's a requirement that the bridge deck be cured with moisture and not with the curing compounds.
So steam curing, tell us about steam curing.
Steam curing is used in the precast industry particularly. The advantage of steam curing is that it accelerates the curing process to over 24 hours or less. What the process is having the member covered and then fill that enclosure with saturated steam, and the temperature is uniform through the member. It also requires, as we've said before, process control. So the temperature has to be controlled, the rate of rise of the temperature has to be controlled, and the maximum temperature has to be controlled. It's very critical that these constraints are controlled because steam can actually damage concrete.
So that brings us to the end of the 5 Cs, but what happens when we don't follow the 5 Cs? Cracking.
Certainly, Peter, and that's what we're all trying to avoid. Basically, most concrete cracks, I think we should make that clear, but what we're talking about is cracks that are of greater width than 0.1 millimetres.
What happens though when the crack is bigger than that? That becomes an issue.
Certainly, when it gets to beyond that size, then we are faced with a problem that aggressive agents could get into the concrete. So the process is that we want to avoid the cracking occurring in the first place.
So during concreting, what sort of cracking can occur then?
In the early stages of concreting, while the concrete is in the plastic state, we get phenomena called plastic cracking. Now, this cracking is not a problem as long as it's noticed because they can be worked on and closed up.
So that's during concreting. What about during the curing process, Don? What sort of cracking can occur then?
If the concrete is dried out, then we get a phenomenon called shrinkage cracking because there's a volumetric change in the concrete as it dries out, and the concrete doesn't have sufficient strength to resist it, so it cracks. And in that case, the cracking has to be repaired. There's no way that you can restore it.
Okay. Is there any other sort of cracking that we need to be worried about? I'm sure there is.
Well, certainly 2 other forms. The first one is thermal cracking. So if concrete in a very immature stage is subjected to changes in temperature, resulting in a contraction or expansion, the concrete doesn't have enough strength to resist that, and so it will crack. And we call that thermal cracking.
Okay, so that's thermal cracking. You also mentioned slump cracking.
Right. Slump cracking occurs when the compaction is inadequate in the concrete. So as a result, the concrete sitting over the reinforcing is hung up where the rest of the concrete consolidates down, and you end up with a crack that follows the line of the reinforcing. And if that happens, you'll find that it may be right through the deck, and the implications may be that the deck will have to be abandoned.
Wow, so that really goes to show how important it is to address the issue of getting the correct slump at the start.
And compacting the concrete properly.
What about the formwork? I'd imagine that has a very important impact on the process.
Certainly the formwork has to be designed to take all the pressures and forces that are going to be subjected to it. We don't want the formwork to be going out of shape, and we don't want the formwork to be leaking slurry, and we do that by having good joints in the formwork. The formwork needs to be rigid so we don't get deflections, and that way you can control the line and position of the formwork. So when you're removing the formwork, you need to take care not to damage the surface, and if people start using tools that are going to abrade the surface, it's going to spoil the off-form finish.
So Don, are there any other avoidable defects we need to be aware of?
Well, other avoidable defects include honeycomb, which may be caused by lack of compaction, but it also may be caused by slurry loss from the formwork. So in other words, the formwork hasn't been sealed properly. You may have cold joints in the concrete where there's been a delay and the 2 layers have not been integrated, so we end up with a line in the concrete surface. You may have burn marks on the formwork as a result of someone touching the form with a vibrator. And you may have foreign materials that have got into the formwork that haven't been cleaned properly. when they should have been before the pour.
Well, what about repairs?
Well, ideally, we don't want to repair concrete at all.
Yeah.
But if repairs are required, then the method has to be approved. The materials have to be approved, and in fact there may need to be a trial patch somewhere else just to see that the method they're going to use is appropriate. And you're going to try to match the colour, obviously, for aesthetic reasons.
So, Don, what is it about the civil construction industry that makes it unique?
Well, what we're on about is building structures that are going to be durable and around a long time after we've left, and that's the way we need to approach it.